Quadratic functions. In this section, we will explore the family of second-degree polynomials, the quadratic functions. While they share many characteristics of polynomials in general, the calculations involved in working with quadratics is typically a little simpler, which makes them a good place to start our exploration of short-run behavior. In addition, quadratics commonly arise from problems involving area and projectile motion, providing some interesting applications. Example 1. A backyard farmer wants to enclose a rectangular space for a new garden. She has purchased 80 feet of wire fencing to enclose 3 sides and will put the 4th side against the backyard fence. Find a formula for the area enclosed by the fence if the sides of fencing perpendicular to the existing fence have length L. In a scenario like this involving geometry, it is often helpful to draw a picture. It might also be helpful to introduce a temporary variable, W, to represent the side of fencing parallel to the 4th side or backyard fence. Since we know we only have 80 feet of fence available, we know that L plus W plus L equals 80, or more simply, 2L plus W equals 80. This allows us to represent the width W in terms of L. W equals 80 minus 2L. Now we are ready to write an equation for the area the fence encloses. We know the area of a rectangle is length multiplied by width, so A equals L multiplied by W equals L multiplied by 80 minus 2L. A of L equals 80L minus 2L squared. This formula represents the area of the fence in terms of the variable length W. Variable length L. Short-run behavior. Vertex. We now explore the interesting features of the graphs of quadratics. In addition to intercepts, quadratics have an interesting feature where they change direction, called the vertex. You probably noticed that all quadratics are related to transformations of the basic quadratic function, f of x equals x squared. Example 2. Write an equation for the quadratic graph below as a transformation of f of x equals x squared. Then expand the formula and simplify terms to write the equation in standard polynomial form. We can see the graph as the basic quadratic shifted to the left 2 and down 3, giving a formula in the form g of x equals a multiplied by x plus 2 squared minus 3. By plugging in a point that falls on the grid, such as 0, -1, we can solve for the stretch factor. -1 equals a multiplied by 0 plus 2 squared minus 3. 2 equals 4a equals half. Written as a transformation, the equation for this formula is g of x equals half multiplied by x plus 2 squared minus 3. To write this in standard polynomial form, we can expand the formula and simplify terms. G of x equals half multiplied by x plus 2 squared minus 3. G of x equals half multiplied by x plus 2 multiplied by x plus 2 minus 3. G of x equals half multiplied by x squared plus 4x plus 4 minus 3. G of x equals half x squared plus 2x plus 2 minus 3. G of x equals half x squared plus 2x minus 1. Notice that the horizontal and vertical shifts of the basic quadratic determine the location of the vertex of the parabola. The vertex is unaffected by stretches and compressions. Try it now. A coordinate grid has been superimposed over the quadratic path of a basketball. Find an equation for the path of the ball. Does he make the basket? Forms of quadratic functions. The standard form of a quadratic function is f of x equals ax squared plus bx plus c. The transformation form of a quadratic function is f of x equals a multiplied by x minus h squared plus k. The vertex of the quadratic function is located at hk, where h and k are the numbers in the transformation form of the function. Because the vertex appears in the transformation form, it is often called the vertex form. In the previous example, we saw that it is possible to rewrite a quadratic function given in transformation form and rewrite it in standard form by expanding the formula. It would be useful to reverse this process since the transformation form reveals the vertex. Expanding out the general transformation form of a quadratic gives f of x equals a multiplied by x minus h squared plus k equals a multiplied by x minus h multiplied by x minus h plus k. F of x equals a multiplied by x squared minus 2xh plus h squared plus k equals ax squared minus 2ahx plus ah squared plus k. This should be equal to the standard form of the quadratic. Ax squared minus 2ahx plus ah squared plus k equals ax squared plus bx plus c. The second degree terms are already equal. For the linear terms to be equal, the coefficients must be equal. Negative 2ah equals b, so h equals negative b divided by 2a. This provides us a method to determine the horizontal shift of the quadratic from the standard form. We could likewise set the constant terms equal to find ah squared plus k equals c. So k equals c minus ah squared equals c minus a multiplied by negative b divided by 2a squared equals c minus a multiplied by b squared divided by 4a squared equals c minus b squared divided by 4a. In practice, though, it is usually easier to remember that k is the output value of the function when the input is h. So k equals f of h. Finding the vertex of a quadratic. For a quadratic given in standard form, the vertex hk is located at h equals negative b divided by 2a, k equals f of h equals f of negative b divided by 2a. Example 3. Find the vertex of the quadratic f of x equals 2x squared minus 6x plus 7. Rewrite the quadratic into transformation form, vertex form. The horizontal coordinate of the vertex is at h equals negative b divided by 2a equals negative 6 divided by 2 multiplied by 2 equals 6 over 4 equals 3 over 2. The vertical coordinate of the vertex is at f of 3 over 2 equals 2 multiplied by 3 over 2 squared minus 6 multiplied by 3 over 2 plus 7 equals 5 over 2. Rewriting into transformation form, the stretch factor will be the same as the a in the original quadratic. Using the vertex to determine the shifts, f of x equals 2 multiplied by x minus 3 over 2 squared plus 5 over 2. Try it now. Given the equation g of x equals 13 plus x squared minus 6x, write the equation in standard form and then in transformation vertex form. As an alternative to using formula for finding the vertex, the equation can also be written into vertex form by completing the square. This process is most easily explained through example. In most cases, using the formula for finding the vertex will be quicker and easier than completing the square, but completing the square is a useful technique when faced with some other algebraic problems.